But again, what we're trying to do is we're going to take large quantities of information. Depending on the area, sometimes those quantities are larger than others. Social sciences, well, psychology. If in psychology we got a sample of like 200-300, it's a pretty big sample, right? I have friends over in econ who are regularly working with samples of over 1 million observations, right? So we're talking about sort of different powers of sort of sample sizes, right? But the main idea is to take something, condense it down, right? So even a small set like this, okay? If you're looking at this, this is the number of drinks per month that a sample of college students have reported, right? Trent, if you look at that and say, and I ask you, so how much does this group of students drink? Just eyeballing it, what would you say?
Just eyeballing it?
Yeah.
On average, 22.
Okay. It's tough, right? So we've got very clear data. It's not terribly complicated data, right? We've just got a count of number of drinks per week. But in this matrix, it's hard to get a sense for, on average, how much are students drinking, right? And so what we could do is we could create a mean. We're pretty close, right? About 15.5 drinks per month, I guess, not per week. A lot of drinks, but in a week. But about 15.5 drinks, right? We could also calculate variance around this, right? We could calculate a standard deviation estimate. Standard deviation of 12.4. That suggests that on average, sort of average deviation from the mean is about 12 drinks, right? So it's pretty big deviation from the mean, right? So we're starting to think about variance estimates. If we wanted to look at range, our range is 45 for this data set. So we've got anywhere from 0 drinks to 45 drinks over the course of a month, right? So these are descriptive statistics that start to give us a better sense for sort of on average how much people are drinking. We could also use graphs. We in psychology are woefully horrible at just representing things graphically. If you look at biological journals, things along those lines, a lot of what they're presenting is in graphs. There's so much rich information that you can provide in graphs. I'm going to force you to use graphs, interpret them, hope you translate that into your own research. But this is a nice picture too, right? 15.4 drinks a month with a standard deviation of 12.4. In my head, I kind of have a distribution, but then we actually throw this up on the screen, and this looks a lot different than the distribution I had in my head. Yeah, but what's going on with this histogram here?
It looks like a lot of people are drinking about 15 times a month.
Mm-hmm.
And about 13 times a month too.
Mm-hmm.
And not a lot of people are drinking like 2 times, like two to 4 times a month.
A lot of people?
Not a lot of people.
Based on the graph here? Well, I guess, so looking at the graph, and no, so like starting to look at modes and things along those lines, right? If I was looking at this graph, I would say, well, it looks like and this is why it's really valuable sometimes to look at these. Does it look like we have one group of people or maybe a couple groups of people? Like, Candace, why are you saying 2 groups of people?
2 because, well, you can see that the majority of people drink between 0 and 30 times, and then there's a smaller group of people that drink between 40 and 60 times.
Yeah. And I might even go farther and break this down. It looks like we've got some no drinkers here, right? People who drink very, very rarely, right? And we've got some people who are in the middle here who are maybe fairly frequent drinkers, some people who are kind of in the middle, and then we've got these people who are really sort of at the tail of the distribution who are very, very heavy users, right? And so looking at, but let me say, that's not the only way you could interpret this, right? You're just trying to look at these data and get a sense for what's going on, what types of things do I have going on in my data. Plotting these scores out can be incredibly important, right? So organizing information, providing our inferential statistics, trying to tease out and see if we have evidence of a systematic relation between a couple of different variables, right? We can eyeball it, but it's tough to tell. Basically, what our inferential statistics are doing is looking at signal-noise ratio. Do we have more signal there than noise, so that we can say, yeah, we've got a pretty good idea that, assuming that there were nothing there, that these data would be unlikely, assuming that there is nothing there, and trying to get a set of procedures for looking at that. So if we say, and again, this is foray into your education and trauma-related research. So we've got 334 individuals exposed to traumatic injury, okay? Of those 334, we've got 248 individuals reporting chronic pain at least 12 months post-accident, okay? So we've got a full sample of 334, 248 of those individuals are experiencing chronic pain, the other portion of those individuals are not. And our research question is, we're interested in looking at the degree to which pain status, either you had a traumatic injury and you don't have pain, or you have a traumatic injury and do have pain, what we want to do is see how that's related to trait level anxiety. Okay? Pretty simple research question. Sean, what we might do if we wanted to test that question?
You could do a t-test.
Could do a t-test, right? And if we do a t-test, we can go through and run those statistics, and this is what it would look like, right? These are actual data, pulled down. We get a t-statistic of 3.46. Our p-value here is less than 0.001. What's this d? Anybody know what that d is? Stephanie, what's that d? What's that? Yeah, it's Cohen d. And what is Cohen's d? Just the label. What is it? What is it? Not interpret it necessarily, but what is it? You don't need to explain it, just like identify what is Cohen's d an example of?
Not necessarily an effect.
Yes, an effect size. Just an effect size.
Okay.
Cohen's d, your d is your effect size. And we'll talk about different effect sizes. This Cohen's d says that on average, or that there is about almost a half a standard deviation difference between the pain group and the non-pain group in terms of their trait level anxiety. Okay, we could also take a look here. So this gives us our statistical test. This tells us our effect size, right? It gives us a metric of how large that difference is. We can also calculate a mean difference. On average, our pain people are reporting close to 6 points higher on our trait level anxiety scale, and we can calculate a confidence interval, right? This confidence interval is going to say, all right, this is the difference, this is the point estimate that we found in this sample. We found for these individuals, we had a difference of 5.73 points on this anxiety measure, but we understand that this is just one sample of an infinite number of samples of this size that could be drawn from the population. So what are the range of plausible values for what this actually might look like in the population? Range of plausible values, we could, based on these data, we could maybe expect anywhere from a 2.5 to a 9-point difference between members of these groups on their trait anxiety. Okay, so just ways to go ahead and look at this relationship. So Sean identified a t-test as one possible way to look at this relation. Any other ideas on what we might do? We also look at correlation, right? It's legal to run a correlation on this. The p-value will be, by definition, identical across these, right? We've got a dichotomous variable and continuous variable. Dichotomous variable, what's our dichotomous variable, Candace?
One with only 2 options.
Right, and so in this example,
values.
what's our dichotomous?
Pain status.
Pain status, right? And what's our continuous variable?
Me still?
Yeah.
Oh, trait. What's STI?
Trait
Chronic
anxiety.
Anxiety? Oh,
Trait
anxiety.
anxiety,
Gotcha.
yeah, right? And so we've got a dichotomous variable, continuous variable. We can run a correlation between that. If we run that correlation, it's 0.4. Again, this is the correlation that we found in these data, recognizing that these are just This is just one sample of an infinite number of samples we could get. So our estimates for plausible values for this correlation, the actual true unobservable effect in the population, somewhere of a correlation between 0.3 and 0.48, and a statistically reliable effect there. This is an ugly correlation graph, right? Because you've got, this is the scores of people without pain, this is scores of people with pain, so that's not terribly useful. But this is one of these things, right? What you need to do, there's often, when you have a question, a number of different ways you could represent that relationship. What you need to decide is which one of these makes the most sense statistically, and also from a presentational standpoint. Like which one of these is maybe going to be the best way to present these data so that people can understand what I'm talking about, right? If we're doing this, we're doing two group comparisons. Generally, the t-test is kind of what people think about, like is this group better than this group or bigger than this group? But correlation is perfectly acceptable, no reason you couldn't do that as well. So these are the types of things we're thinking about in terms of decision making. The other thing we're doing, offering standard language for professional communication. If I'm doing my research here in my lab and I want to collaborate with investigators in Korea, and sort of being on the same language, and this in terms of what we did, this is the fact that we found, statistics is a nice language to say, okay, I see and know exactly what you did and can go through and replicate that. I think this is an important thing, again, sort of moving people past this idea that, oh, what's my statistical package, what's my numbers and things like that. More important than this is knowing what your statistics are, how to execute those, and how to interpret those appropriately, okay? Do not report statistics found on a printout without understanding how they were computed or what they mean, all right? Just because a program gave those to you, you can't assume that what you did is what you're actually looking for. Who's working with Sean McRae? Yeah, so Sean and I were talking about it. So he ran some analyses in SPSS, and then he ran some stuff in R and was getting different outcomes. Now Sean's a smart guy, and Sean says, oh, this is a problem, right? And then went through it and took a look and tried to figure out what was going on, why they were getting a discrepancy between those two, right? What you get sometimes is people like, oh, this is the numbers that I was given, and so I'm just going to go ahead and I'm going to report those. If you have any understanding what those numbers mean and how to interpret those, you would recognize that those things are ridiculous. Okay, so looking at a paper a few weeks ago, and someone reported Cohen's D of 8. Right? And I was like, that would be awesome. So, but you're saying that this group is 8 standard deviations larger than this group. Those two means don't seem 8 standard deviations apart. Go back, go ahead and check this, right? But this is why it's important to know what you're doing, so you're not putting stuff out there that clearly makes no sense, but you are paying attention, right? Also, take efforts to assure underlying assumptions are reasonable given what you're doing, right? SPSS statistical programs will do whatever you tell them to do, right? That doesn't mean the results that you get and the output that you get makes any sense, right? And you see this all the time. People say, oh, I'm going to run, see if these two groups differ on that thing, right? When your continuous outcome variable coded 1 to 7 are different brands of soda or something like that, right? The mean of your 1 to 7 soda scale doesn't mean anything, right? Because 1 is Pepsi and 2 is Coke and 3 is whatever. Like that, it doesn't have any meaning. Now SPSS will tell you that there's a difference or there's not. This is the difference, but it doesn't actually mean anything, right? So you need to know what's going on and how this all fits together, okay? So again, and when you get those results, even if you've gone through, done everything right, making sure that your procedures were correct, when you're taking a look at your effects, right? And you're like, all right, this is what these data are saying to me right now. Things to think about: credibility, generalizability, and robustness. Right? A lot of this stuff breaks down into your design. Okay? A lot of people come and say, oh, well, I did this, but that's all wonky with the design, so how do I fix it with statistics? You can't. Like, crappy data is crappy data. You need to make sure you're collecting good data on the front end, and then we can have a discussion about how you go through and analyze those things. based on what you've got, do these results make sense? Is this something that makes sense within the context of the area that you're studying, right? I go through and I run an analysis and I see that I've got a strong positive correlation between post-traumatic stress disorder and general happiness. Does that make sense? Nope, it doesn't make sense. Probably what happens is there was something that up means down and down means up. Higher scores indicate lower happiness or something like that, or I didn't score something correctly. That should be a cue for me to go back through and take a look and check to see what I've done makes any sense, okay? Also, generalizability. Okay, I found this for this group. Can I expect these effects to generalize to other groups? And robustness, right? I found a difference of P equals 0.0452, right? Technically, I can claim I have a statistically significant effect, but that's pretty slim, right? What's the size of this effect, and would I expect this to generalize, or is this maybe something that happened to be a sample-specific effect in these data? And we'll talk about that as we move through some of this stuff. Questions? All right. Basic terms, concepts, things. Population, okay? We're talking about a population. This is all individuals, units of interest that we are hoping to generalize our results to, okay? Populations specific to the study, all right? There's not one population out there. There are an infinite number of populations. It's up to you to define your population of interest. Someone give me an example of populations.
If I'm looking at all 10th graders across the nation, then 10th graders across the nation.
Perfect. 10th graders across the nation. Which nation? The U.S., whatever nation you care about. These are members of the population of interest. This is who I am hoping my results will generalize to. Someone else, another example of a population.
All criminals that pass through the court system.
Okay. Criminals that pass through the court system. Now we got some subjective, like
Anybody who goes to court, period.
anybody who goes to court, period. There we go. Like, who's to say criminal? Yes, no,
I will
things along those lines,
clarify my
right?
population.
Individuals involved with the criminal court system, right? That's another population, all right? But as we start to go through, we can start to be very specific when we're looking at experimental stuff as well. Like, my population might be the hypothetical population of all individuals who receive this experimental manipulation, right? If I'm looking at the effect of this, say I've got some sort of film stimuli that I watch people in order to induce sadness, right? My population is then all individual, and I'm looking into see whether or not sort of this film stimulus makes people more sad than this film stimulus, right? My population of interest then is every hypothetical person who could watch this and report on it versus all the hypothetical people in the universe who could look at this and watch this. Same thing with clinical folks, treatment people in my population. Maybe it's every individual who goes through cognitive behavioral therapy for depression, this specific package. Now, this might be a new treatment, and maybe only 5 people who have ever received it, right? That's my sample, but the population that I've drawn from are all people who could potentially receive this individual treatment, right? And so thinking about your population, we don't do it a lot, we should do it a lot, but it starts to become relevant in deciding, is this a generalizable effect? Who am I hoping that this research extends to, okay? APA task force, again, one of those articles had you read. Interpretation of results of any study depends on characters, population for interest, or population intent for analyses. Define the population, participants, stimuli studies very clearly. We don't do this. We should do this more often. Be thinking about who the population is that we're looking at or trying to generalize to. Sample, okay? Our sample subset of individuals selected from the population, all right? Random sample is our gold standard. How often do we get a random sample of the intended population? Next to 0, almost never, except in very, very data, right? Looking at random digit dials or random selection of individuals in the country, right? Are those true random samples? No, right? Because there's people outside the sampling frame. There are people who you can't access via email, telephone, mail survey, things along those lines, right? Are the people who respond to those a random set of people? No, right? So this gold standard of random sampling is very, very, very difficult to achieve. What does it mean if we say, I've collected a random sample? By definition, what is a random sample? What do you think, Candace?
A random sample is a sample in which everyone in the population of interest has an equal and likely chance of being selected.
You're reading it out of someone. It's perfect, yeah. Every single person has an equal chance in being included in the sample, right? That's what we're talking about, a true random sample. It's so difficult to achieve. I don't even know if I can think of off the top of my head an occasion in which this happens, unless my population is people in this class. That's my population of interest, right? And I were to go through and randomly sample you, that I guess would be a random sample, but we've gone through and restricted our population to such an extent that, you know, may make sense depending on the research question, but in applied style, very difficult to achieve. In general, bigger samples are better samples. Why is this? Jack, any idea?
Well, I mean, larger sample is when you get closer to your population.
Yeah, exactly, right? As our sample size starts to increase, the precision of our estimates start to get more and more tight, right? If I have a random sample, if I'm interested in the average height of Americans, and I randomly select 5 people, and it is truly random, and I take the average height of those 5 people, I'll get an estimate, and it's the best estimate I can create given the 5 people that I've selected, but I'm gonna have a much, much more precise estimate of this true hypothetical figure of the random height of American citizens if I have a sample of 500, right? My standard error of that estimate is gonna be much more narrow the more people I get, right? Bigger is better. I'm getting more people, I'm getting more observations, and I'm also collecting people who are probably out in the fringe, right? If I'm thinking about average height, I'm probably, in that sample of 5, I'm probably not gonna get anybody who's 7 foot or taller, and I'm probably not gonna get people who are quite small, say, under 5 foot, right? Just because those are low probability captures in a small sample, they're still part of my sampling frame, they're still part of my population, right? With our larger samples, we're catching those people and we're being more precise. When we're talking about our statistical inference, it's very important that this is such a fundamental concept of statistics, and I think we forget it a lot of times. Population, these are everybody who you're interested in, right? These are all the people, if I'm doing a study, maybe it's all people who have experienced trauma, period. Like anybody who's experienced a traumatic event, that's my population, right? Now, I obviously can't measure all people who've ever experienced a traumatic event, so what I do is but I can get a sample of those individuals, right? And so I get a sample of individuals from this population who've experienced significant trauma, and I can study those because I have access to those. Now, if this is a large sample and it's a random sample, that's better, and that's what we're assuming. We always violate this, right? And so that becomes a problem. We have to start thinking about that. What we do with that sample is we go ahead and run some statistics, and from those statistics, we're making inferences about the population. So my sample, this is why it's so important to have a good sample, a reasonable sample, because I'm making inferences about the population based on the statistics I ran on the sample. We're gonna get this, and when we start talking about hypothesis testing, this is gonna be very important. Some of you guys are gonna have slips, and I'm gonna catch you. When we're talking about hypotheses, who are we interested in with respect to our hypotheses? Are we interested in the sample or the population? The population, right? It's nonsensical for me to say the difference between group A and group B in my sample is 0, because there's always going to be a difference, right? Like I don't actually care. That's a ridiculous statement. I know I don't have to test that. I can say what's the height of this group and what's the height of that group. Unless they're exactly the same, then yeah, that's a ridiculous hypothesis, right? The hypothesis isn't about the sample, it's about the population. is there a large enough difference in my two groups within my sample that I can then infer that there's probably a difference in these hypothetical populations across these two, right? So again, population, who we're talking about, the sample is what we can get, run some statistics in order to make inferences on this unobservable population that we'll never capture, and sort of getting at these hypothetical parameters out there in the universe. Hypotheses, never about the sample. Okay, something to remember, right? So the mean of this group is bigger than the mean of that group. Nope, that's not what we're looking at. We're saying the mean of the population of men is different than the mean of the population of women, right? That's who we're looking at. We're not saying the men in my sample are different than the women in my sample, because they're clearly different, because I can see it on paper. I don't need to run statistics to tell me that, right? What I want to see is whether or not that difference is large enough to infer differences in the population. Questions? All right, variables. Pretty straightforward, but just make sure we're on the same page. Variable, character, condition, changes or had different values. If I have a factor that does not change, or all my values are the same, that is a constant, it's not a variable, right? Constants are bad news. You don't want them. You're hoping you never collect something that's constant. We need things to change around a little bit in order, otherwise our statistical models fall apart, okay? Parameter, this is a characteristic. This technically, if we're being precise with our language, a parameter refers to a population, okay? So the average height of men in America, that is a hypothetical parameter. It's a value attributed to the population. Now, we can't ever observe that directly, but it's a theoretical value that's out there in the universe, generally indicated through a Greek symbol. A statistic, that's a characteristic that describes a sample, okay? So if I go through and I collect a sample of American men and test their height, and I have a mean, the average of their height, that's a statistic, okay? And we generally use our Arabic letters there. We work with our statistics because the parameters are unknown. We can never observe our parameters, but theoretically we can get infinitely close to actually measuring those if our samples are large enough and our measurements are precise enough. Questions about variables, parameters, things along those lines? This is where things got to start to get a little bit tricky, okay? Descriptive, or no, this is straightforward. Descriptive statistics, what we're just trying to do is we're trying to summarize data with graphs, averages, mean, standard deviations, things along those lines. Those are our descriptive statistics, okay? So here we've got a boxing district plot for something that someone was measuring on through little absences. This would be an example of a descriptive statistic, okay? Inferential statistics, these are the statistics that are horribly flawed, as you read about, but the best thing we have in most cases for trying to tease apart signal and noise. Am I seeing a difference between my two groups because there's an actual difference in these hypothetical populations, or is the difference that I'm seeing just random variation and error in my sampling stuff? Okay. Our inferential statistics are things like correlations, t-tests, ANOVAs. Our inferential statistics are the things that give us p-values and stuff, right? You don't have a p-value or a mean. A mean is a mean. A standard deviation is a standard deviation. We're not getting p-values to histograms. Our inferential statistics are where we start to give those, take a look at those tests. All right, where things get a little bit tricky. I will beat you over the head of this is all semester long. Sampling error, okay? Sampling error is the error discrepancy between a sample statistic and the population parameter. Okay? That's all sampling error is, all right? We've got this hypothetical unknowable population parameter that's out there that we're trying to get at, right? And so we draw a sample and we get test that sample and we get a measurement of the mean of this sample. Our sampling error is the extent to which our sample mean that we've observed is different from the actual population parameter. The discrepancy between those two things, that's your sampling error. That's all sampling error is. It's the difference between your statistic and the actual parameter. That's your sampling error, okay? we design our samples to be representative of the population, hopefully, right? But this is very, very difficult. It's impossible for our sample to be exactly reflective of our population of interest. Oftentimes people are like, well, sampling error is what happens when you collect a bad sample. Absolutely not. Absolutely not. Sampling error happens always because our sample statistic is never going to be exactly the same as our population parameter. It's never going to happen, okay? So all samples have sampling error. We always are dealing with sampling error. Sampling error is never going to be zero, but all sampling error does is reflect the difference between what we've observed and the hypothetical value, and what we're trying to do in research is trying to make that difference as small as possible. Okay. So, for example, my population is 1,000 college students. All right, these are the only people in the universe I care about are these 1,000 college students. Okay. Population parameters, I can do this because I've got a very circumscribed population, and I guess in this example, I was able to get a hold of all these 1,000 people. And my sample has an average age of 21.3, average IQ of 112.5, 65% female, 35% female, or 65% female, 35% male. I collect two samples. Let's say I've got a sample of 100 in sample 1, a sample of 100 in sample 2, right? Well, I guess not 105, whatever. So to go through and collect these people, so these are my sample. Got a sample of 5 people in each. Of these individuals, we get an average age, an average IQ, and a gender breakdown, average age, average IQ, gender breakdown. Okay? Are these samples identical to one another? No. Are these samples identical to our population parameters? No, right? This is our sampling error. I could have, now you can criticize my sample for being small, fair enough, right? But even if I go through and I randomly sample 5 people, even if it's a large sample from this 1,000, I'm always going to get some discrepancy between my population parameter and my sample statistic. That discrepancy is your sampling error, okay? So divorce this from your head that, oh, sampling error is what happens when we collect crappy samples. No, our sampling error gets worse if we collect crappy samples or have bad measurements, but sampling error is always, it's a constant, it's always going to be there. It's in the background of all our statistical calculations. So just know all that we're talking about with sampling error is the discrepancy between my sample statistic and my population parameter.
Okay, this might be a really dumb question.
No, it's not. It's going to be an excellent question.
So say you have a population that's small enough to where you can actually include everyone
Mhm.
at some point or another in your sample.
Mhm.
Everyone is only tested once, but you include everyone, so everyone is
Mhm.
included. And so you know the population parameter, and then you get, the sample statistic. Now, even
Okay.
though you've included everyone,
I'm gonna stop you
shouldn't
there.
you still have sampling error possibly due to random error?
No.
So,
Once we can measure the entire population directly, we no longer need statistics.
okay,
Because all we're doing is we're working with norms, right? Let's say that I have so that this classroom and that classroom are my two populations. So my population involves 3rd graders in Miss K's class and 3rd graders in Mr. T's class. That's my population. No one else makes any difference, right? I no longer need statistics. I can
Okay.
just say, what's the discrepancy between this group and that group, and then that's what it is, right? Because the whole purpose of our inferential statistics is to infer something about a population. If I can directly measure the population, statistics go out the window. I don't need it anymore, right? Because is there a significant difference between this group and that group? I don't know, those are my populations. I can actually measure the exact effect size for the difference between those two populations, and it's a Cohen's d of 0.2, right? This population is 2 standard deviations above that, or 2/10 of a standard deviation above that population. And that's it. But it doesn't matter, and it's not 0. I don't have to infer whether it's 0 or not because the number's not 0, it's 0.2, right? And so that's from a theoretical standpoint, what we're working with, if we're just working, if we do actually have access to the populations of interest. Does that make some sense?
Oh, yeah.
Okay, cool. Great question. And this, but unfortunately, this almost never happens, right? So even
Right.
if I'm applying some sort of reading intervention to Mr. T's class and see how that contrasts with Ms. K's third grade class, sort of theoretically, the idea is that I'm not just applying it to these people, is this a useful thing to do for third graders more generally, and then all of a sudden, that's my population, and then I can run statistics to see if there's a difference. Questions on this? All right. Factors that impact sampling error. All right. Our goal in research is to try and make our sampling error as small as possible. Things that we can do to reduce our sampling error: increase sample size. As our samples get bigger and bigger and bigger, they get more and more representative. Our error gets very, very small. Our error starts to get more precise as our sample size increases. Sample selection. Random samples are better than non-random samples. We start to remove the possibility of bias. We start to avoid missing certain sections of the population that we might not get otherwise, right? Random samples are always better than our convenient samples, which is almost always what we're doing, right? Anybody who plans on using the participant pool for their research, that's a convenient sample, because these are people you are able to capture, right? Even if your population of interest is college students, people you're getting through this participant pool are not a random sample of college students. They're students who are taking, at this university, taking psychology courses, right? But to the extent that we can get larger, more random systematic samples, the better. And then our measurement tools, right? I'm going to say that I'm interested on the relation between extroversion and weight, okay? So I bring people in and I have a state-of-the-art measure of extroversion, and I say, all right, this is measuring people's level of extroversion, and then I want to get a sense for how much people weigh. And so my measure of weight is I go up behind someone, kind of pick them up and be like, like $130, right? My measurement tool for weight is awful, right? And so I'm going to have horrible, horrible, horrible sampling error on a function of my measurement tool, right? This is why we start to forget this a lot of times, like, oh, I'm just going to use any old measure to measure something. Well, you can do that, but you're introducing a whole lot of static unless you've gone through and taken a look at psychometric research, making sure that this is a good measure of the construct that you're trying to capture. Right? Now, sometimes we use proxies, right? Like I want to look at the relation between intelligence and income, right? And so my proxy for intelligence is your grade in high school, right? Your high school GPA. Is high school GPA a good measure of intelligence? Better than other stuff that you can get, but it's certainly not the best, right? Because there's so much other stuff going on. Your measurement, your metric there has a lot of measurement error in there, and so your sampling error is going to be pretty huge. Questions on sampling error, the things that influence sampling error. All right. Methodology is huge, all right? And this is why as you're going through and designing your studies, you need to be thinking about, so what types of things are going to go in and start creating static in my study. Static is bad. Static is going to systematically decrease the likelihood that you're going to find what you're hoping to find, because there's a whole lot more static to your signal. So this involves training your graduate students to run things effectively and consistently and not doing whatever the hell they feel like, right? It's making sure that data is entered correctly and going through making sure you don't have weird scores that don't actually fall on the metric that you're looking at. Making sure that people aren't running things with jackhammers in the background while people are trying to take attention tasks or things along those lines, right? These are all the things, and this is why it starts to become important to have good controlled research, because it's you're only shooting yourself in the foot from a statistical standpoint, unless you either have massive samples or huge effects. Okay. Theoretical constructs. This is important. Construct.
like an attitude toward an idea. I'm trying to think of a more specific example. Like somebody's background or I just blanked, I'm
Yeah,
sorry.
no. So attitudes towards spending or investment or sort of purchasing or something like that, right? Somebody else give me a construct. Yeah,
Intelligence.
intelligence, right? Something else. Motivation, right? These are all constructs, right? These are things that we can't see. We think they're things, right? So we've got this thing, I was looking over there, I've got this construct called statistical knowledge, right? I can't hold your statistical knowledge. The best thing I can do is try and put together a measure that should tap fairly specifically into your statistical knowledge, right? So the construct itself, though, we can't observe these things directly. So what we have to do is try to come up with measurements that we can tap into that construct and use that to describe, explain behavior, okay? What starts to become important when we're developing constructs is having an operational definition. This is telling us what the measurement of this observable behavior is and uses this to define the construct, okay? So if I say my construct is height, right? How might I operationalize height? What do you think, Inch, right? My operationalize is a physical measurement of height in inches. Now, we're all pretty comfortable and everybody's sort of in agreement with what constitutes height, right? But as soon as we get into psychological research, if we're talking about even things like motivation, but what is the accepted definition of motivation? I don't know, right? There's a billion of them, right? And different people have different ideas on how we should operationalize motivation. And our operationalization of a construct may differ from study to study. If I'm working in a school district and I say I'm interested in studying aggression, what I have to do is then operationalize aggression. What types of things count as aggression for my study? Now, I could give students a paper pencil measure and have them report how aggressive they are. And so maybe my operationalization of aggression is scores on this specific measure. Or maybe I want to do some behavioral thing, and my operationalization of aggression is watching how many aggressive acts students engage in. But if that's my operationalization, then I need to start to define some boundaries on what counts as an aggressive act and what doesn't count as an aggressive act, right? And so, again, this is one of these things. You say, oh, I'm studying PTSD. Well, it seems to me that what you've done is you've got a self-report measure that you're saying that the scores on this measure reflect post-traumatic stress disorder, but that's a different thing than the construct itself, and that measure may or may not be a good indicator of the construct that we're interested in based on what we know about what we've got going on, okay? So, as an example, in graduate school, I put together a paper we were interested in was driving anxiety construct. We had a clinic we were working with survivors, members of the community who had been in multiple car accidents. They were coming in, we were doing diagnostic screenings and things like that. One of the things that people were doing would report some crazy stuff that they were doing when they were driving. So these are people who've been in an accident, terribly concerned about getting in another accident, very fearful. A lot of the things they were talking about in terms of driving behavior as a function of anxiety were things that objectively put you at greater risk of getting in more accidents, right? So driving 20 miles under the speed limit all the time is to be safe. That's fine, but if you're on the interstate and you're doing 20 miles slower than everybody else, people aren't expecting that. You're probably going to get yourself in an accident. Or I'm driving on the far shoulder of the road. Like seriously, like the line is sort of dead center. That's where I'm driving. That's not a safe thing. Or I'm terrified of getting hit, and so instead of paying attention to what I'm doing, I'm looking constantly in my rearview mirrors to make sure no one's going to come hit me when I need to be paying attention to what's going on in front of me. One of my favorites, like very concerned, very angry and upset with unsafe drivers or people who I perceive as being unsafe. So while I'm driving down the interstate, having a pad and a pen and a marker next to me so I can speed up and write, "You are an unsafe driver," and post it on the window so that you can see that you are being unsafe, right? All these anxiety-generated behaviors, right? And obviously problematic, and right, this is a phenomenon that could be interesting to take a look at. But what we need to do first, if we're going to say anxious driving behavior, I've got a lot of examples, but examples aren't an operational definition, right? And so for the purposes of this paper, put together an operational definition of anxious driving behavior. For the purposes of this research, anxious driving behavior is conceptualized as an excessive increase, decrease, or disorganization of behavior occurring as a consequence of anxiety during the operation of a motor vehicle. Behaviors of interest may be, but are not necessarily reckless, inappropriate, or dangerous, right? So we've got this stuff that we see as maybe a construct, right? But then what we have to do is say, all right, we want to measure it, study it, but then we have to give an operational definition for what this actually is, okay? Very, very important. And when you're going through and looking at research, oftentimes people say, oh, well, this is a study, we're looking at the relationship between positive affect and relationship formation, which is fine until you actually look at how they've measured positive affect and you say, okay, is that what you're actually measuring, or are you measuring something else, right? The statistics may be fine and make it look wonderful, but it's up to you as a critical evaluator of research to make sure that the constructs that they've identified are actually a reasonable reflection of what they've actually measured, right? Measurements are fallible indices of hypothetical constructs. If your measurement's crap and you're not measuring what you say that you're measuring, the statistics don't matter at all, right? So something to think about as you're going through and looking at research and putting this stuff together. Operational definition is important for implications of statistical inference. Again, we're performing analyses on numbers that are imperfect indicators of our constructs. Our analyses are only good as our measurements. If we've got crappy measurements because we've had poor methods, that doesn't fix. I can't magic some statistics up that fixes the fact that you measured something other than what you were trying to measure in the first place, right? I can't covariate things for that, right? So it's important to be thinking about that as you're putting together your own research, evaluating the research of others, things to keep in mind. Questions about this? All right. Discrete and continuous variables. This is where things start to get a little bit tricky. Discrete variable. All right. If we're talking about a discrete variable, we're talking about some measurement that involves separate indivisible categories. All right. There's no way we can have a value that falls in between neighboring categories. Right. So examples of discrete variable: numbers on a dice, numbers of children. This is again one of these things where we hear this all the time, but it actually doesn't make sense from a research standpoint. People have 2.5 kids on average. Children the number of children is an ordinal variable technically. There is no such thing as a half of a child that you just keep in your home for your own purposes to be the average family. If you have a half a child in your home, you're not the average family, certainly not the average family, right? So, but we'll hear about this a lot, right? I have, 3.2 bedrooms in the average house or something like that, right? Like a 0.2 bedroom is not a real thing, right? And so this is what happens when we start assigning sort of the inappropriate statistics to inappropriate levels of measurement, okay? This is another thing too when you're thinking about in choosing statistical analyses and how we're going to evaluate this. The number one thing you should do, is you should say, what are my dependent variables, what are my independent variables? That's the number one thing to do. And then ask yourself, what's the level of measurement of these variables? You do those two things, that's going to winnow down your possibilities for statistical analysis significantly, right? So if you've identified discrete variables, we're talking about dice, number of children. Someone else give me a discrete variable. Countries, right? If I'm looking at marketing or trade, like country's not. I can't have half of China, or 3/4 of Russia, right? That's not a thing. Like, it's the country, it's a discrete category, right? Discrete variables are in contrast with continuous variables. Continuous variables, infinite number of values fall between any two data points, okay? I can take my continuous variables and I can increasingly chop them up into increasingly small pieces that still make theoretical sense, right? Things like time, mass, temperature. I can go down to a half a degree and a half of that degree, down to a millionth of a degree, which is a reasonable unit of analyses for certain types of sciences, right? And I can get that down. This is what we're talking about in terms of continuous variable, okay? So broad sort of groups are discrete variables that are separate individual categories, continuous variable, infinitely number of close reductions that we can get. In actual practice and how we use these, this starts to get a little bit murky. In theory, very clear, straightforward. In practice, starts to get a little bit more difficult. What we have when we're thinking about levels of measurement and variables is trying to identify sort of where we've got, sort of what's the quality of the measurement that we have for our variables. If we're measuring something on a nominal scale, okay, these is a set of categories with different names. Nominal names, these are things that have different, these are just separate things that are just different with no natural order, okay? We label them, we categorize them, but there's no inherent order to your nominal variable, okay? We can look at levels of our nominal variables, and we can say this one's different than that one, but we have no information in terms of analyzing direction or magnitude of the difference between our categories, right? Because there's no inherent order between our nominal variables. So Sean, give me an example of a nominal variable.
Political party.
Political party, perfect, right? I can identify you as Republican, Democrat, Independent, Democratic Socialist, like it doesn't, like all sorts of things, right? But there's no natural order to that. Now in my data set, I might label them 0, 1, 2, 3, 4, and if I plug it into a statistical analysis, it'll run a correlation for me, but it doesn't mean anything, right? Because these are just individual categories, right? Same things like brands of laundry detergent, right? Or countries are a nominal variable. Things along those lines that there's no inherent order to these things. What ends up happening is then people start running means on ordinal variables because they're coded as numbers in your data set, but then the results you get are nonsensical. They don't mean anything. Next up, in terms of this, we've got our ordinal scale. Ordinal scale, series of categories. They're discrete categories, but our ordinal scales have some sort of reasonable and understandable sequence, okay? We see our observations ranked in terms of size and magnitude. So if I have something at this category, it's less than something at this level of our category. Our ordinal scales have inherent direction, but no standardized magnitude, okay? So that says I can rank this first, and this one second, and this one third, but there's nothing to say that the difference between second and third is the same as the difference between first and second, okay? Differences between our ordinal scales are not necessarily equal. Okay. Someone give me an example of an ordinal scale.
Because scale.
What's that?
Because scale. So scale.
I'm sorry, what's that?
I don't remember.
Likert scale.
Likert scale.
Oh, yes, absolutely. A Likert scale. Why is Likert scale an ordinal scale? Seems continuous, right? It was 0, 1, 2, 3. I can put you in the middle of that, right? Why would we consider a Likert scale an ordinal scale?
The difference between values aren't necessarily equal.
Exactly, right? So I can say, how happy are you? And have you rate that on a 0 to 10 scale. And I might treat that like a continuous scale. There's nothing to say that for you, the difference between 5 and 6 is the same as Zach's difference between 5 and 6, or that your 5 is even the same thing as someone else's 5, right? We pretend that it's a continuous scale, but it's actually not. It's an ordinal scale, right? Any other examples of an ordinal scale? Counts, right? Anytime you count something, that is an ordinal scale. Right? There's no difference. Like, so we still have individual. I can't have 7.5 students in here. Like I either have, we're sort of one or the other. Right? There's no half in between type of students. Anytime we get count data, that's an ordinal scale, right? I know that this many is more than this many, but in terms of the value added between this one and that one is not systematic, and there's no differences that I can't break that down into an infinitely small scale. So counts technically are given as examples of an ordinal scale. Any other examples people can think of? Self-report, count data, sports rankings, music charts. I'm number 1 on the top 20 hits, right? But the number 1 and the number 2, there's no like, I'm like 2.5 on this, and there's nothing to say that 2 is twice as popular as 4, and 4 is twice as popular as 8, right? It's just a rank ordering of things. We graduate to an interval scale when we have a set of ordered categories of the exact same size and exactly equal intervals, okay? Distance between intervals on the scale are all equal, okay? The thing that makes up the interval scale is that we have a 0 point that's arbitrary, all right? And 0 point is arbitrary, meaning that 0 does not indicate the absence of whatever the construct is that we're measuring, all right? Someone give me an example of an interval scale.
Temperature?
Temperature, specifically what type of temperature?
Fahrenheit?
Absolutely, Fahrenheit, right? It's a continuous scale. We can break it down to infinitely small units, and the difference between 10 degrees and 20 degrees is the same difference as the difference between 100 degrees and 110 degrees, right? But why is 0 Fahrenheit an arbitrary point on that scale?
Not an absence of temperature.
Absolutely, right? And so when we're talking about temperature is a great example of an interval scale. Anybody else have an example of an interval scale?
Height?
Height?
Yeah.
Not exactly. Okay, height's because what does it mean if I have height of 0?
You can't have a height of 0.
Something could have a height of 0. Well, I guess.
Oh, well, I'm thinking about, human height.
Okay, human height, right?
I guess
But-
I could have been a little more
Right,
specific,
right.
but-
But still the construct of height or length or mass, those things, if it's a value of 0, it means there is none, right?
Right.
And so those are going to be a different type of scale we'll get to in a moment.
So that would be-
What about IQ? On an intelligence score, like your WACE score or something along those lines. Or your GRE score, right? We may have equal distances between those, and we can have equally small things, but a value of 0 on an IQ scale doesn't mean that you are without intelligence. It means probably someone applied a test to a population they weren't supposed to, or didn't know what they were doing, or something along those lines, right? If you have an SAT score of 0, it doesn't mean that you have 0 achievement. It means that something weird probably went on with that, right? So these types of scales where 0 itself is arbitrary in this scale. Ratio scales, these are interval scales with an absolute 0 point, right? So these are going to be things like height, mass, 0 degrees Kelvin, right? Where 0 degrees on that scale means that all molecular motion is stopped. That is literally an absence of the construct in which we identify as temperature, okay? But all of this stuff starts to get a little bit tricky. If we're thinking about our variable type, we've got our discrete and our continuous. Discrete variables are generally our nominal and our ordinal scales. Our continuous scales generally fall in this interval ratio, right? But oftentimes we're using those ordinal scales and treating those as if they were continuous. I'm giving you a 0 to 5 scale on your level of happiness. From a statistical standpoint, we can generally be very aware that what we're doing is we're treating an ordinal scale as a continuous scale and sort of thinking critically about whether or not that makes sense given what we're trying to do for this study. okay? Particularly if we are saying, oh, the relationship between this ordinal scale and that ordinal scale is linear. Well, maybe it is, but maybe if we're looking at something like your scale of aggression and overall functioning, maybe zero aggression and maybe a little aggression, but as soon as we start jumping up to 2, 3, 4, the problems that that may cause with our functioning in human society might start to get increasingly worse, right? And so thinking about not everything has a linear relation, particularly if we're not using continuous scales, right? So in general, and again, this is important not just because this is a fun fact to know and hopefully it comes up at bar trivia. When you're thinking about the types of analyses that you want to run, these are important things to think about. You say, all right, what are my independent variables? What are my dependent variables? What's the level of measurement of those variables? And then let's go ahead and then choose an analysis from there, okay? Also remember that we have differences. We can have a construct that's a continuous construct. I would say PTSD severity is a continuous construct, right? We can have no PTSD severity and increasingly severe symptoms, and we have a wide continuum. We technically fall at any point in the hypothetical scale, but maybe our measurement of PTSD is dichotomous. It's, do you meet criteria for diagnosis or not, right? And so recognizing the difference between the level of measurement of your construct and the level of measurement of your actual measurement, right? And thinking about whether or not that makes sense. As we get into 5300, we'll talk about sort of some of the drawbacks of taking a continuous scale and saying, ooh, yeah, we're just going to split this into high and low and call that good, right? There's a lot of problems with that. It can cause bias. You're losing a lot of information. You can create problematic, spurious relationships and things like that. So these are things that you have to be thinking about on the micro level if you want to make strong interpretations from your data. Questions about this? All right. Again, crucial for selecting your analytic approach here. Mathematical notation, X, Y, Z's, stuff like that. Variables generally, just lay those out as variables. Cases level of a variable, then we start to get into subscripts, people start to freak out as soon as they see something, like people go nuts, like, ah, it's a subscript, I'm confusing me, I sort of run screaming. Don't let it, it's just saying, this is my first predictor, my second predictor, my third predictor, all the way, now we got letters, subscript to letters. I had a panic attack. It just means that we have some sort of open-ended number of variables that we could have in there. Person 1 is X1, person 2 is X2, person 3 is X3, if we're assigning the subscript to individual variable or individual observations. We can also have variable level 1, Z1, Z2, all this. So I have like 3 experimental conditions, right? So just wanting to take a look and see what that notation reflects as you're going through and looking at stuff. N, big N, number of individuals, scores in a population. Technically, we end up using N as the total, our big N is our total sample size for purposes of research because we actually never know the number of individuals in our population. To make it kind of a nonsensical thing to talk about, but technically, this is what your large N represents, but we'll often use it as our total size of our sample. Small N, number of individual scores within a subset of the sample. Sigma, again, something that makes people crazy and will make them terribly terrified. Sigma just means add up all the things after sigma, right? So if I had sigma x1, x2, x3, it just means add up the values of x1, x2, x3 for everybody in the sample. You've got that going on. Okay. Final thoughts. Some nice quotes. So this is a subject, not merely cut and dried set of facts, but rather a set of facts put together with a variety of differences, with a variety of interpretations and opinions. All right. I might look at the same set of data and the same set of analyses and come up with very, very different inferences from that than someone else does, okay? There are just, when you actually get into doing this stuff, it's not like, oh, this is the t-test and this is the only way to look at it. As you'll see, there's this huge level of nuance on terms of how you create your standard error term and what your variance estimates are, and do you include people or not, and is this person an outlier or not, or all sorts of decisions that you have to make, and all of those things can fundamentally impact the results that you end up getting, right? And so you thinking about this as being, you don't want to go to your mechanic and they're like, hey buddy, is there something wrong with my car? And he comes back, he's like, yeah, it doesn't work. You're like, well, I know that, right? What I brought it to you is to go through and start to tease it apart, and hopefully you understand why it works or why it doesn't work, right? Not just, like, I plugged it up to this thing and it says it doesn't work, so I guess you have a non-working car, right? It's not useful. As applied researchers, your job is to get in, understand the nuts and bolts, and be able to play around, and if something goes wrong, be able to problem solve and say, this is why things are going wrong. Or if things have gone too right, you get effect sizes of 8. Also understanding that that's probably problematic and you need to go through and take a look at stuff. One of my friends, Dr. Robson Glasscock, they are statistics, we are not their people, right? Like, you are in charge of the statistics you run and interpreting them and making decisions. This isn't just okay, I'm just gonna go through SPSS and accept whatever I get from the program. You can't fix analysis by design. And again, thinking about very carefully, and we'll give you all sorts of horrible examples of data that are terribly flawed, but we'll use them for illustrative purposes. But thinking about as you're constructing your own research, thinking about very clearly what the constructs are, how am I going to measure those, and then how is that measurement going to map onto some types of analyses that I might want to take a look at. My graduate student Ryan is working on trying to work with attachment constructs, right? And the model he's working with has, say, 4 different categories of attachment, right? And what he's interested in, one of his thesis questions is whether or not attachment remains stable if it's reported by your caregiver when you're, say, 3rd grade and you reported attachment now, right? Well, what happens is if we've got attachment, and we're measuring attachment as 4 different categories, what type of variable do we have? What's our level of measurement? I guess maybe maybe for the Psyc people, sort of in terms of attachment, right? I have 4 different attachment categories. What type of variable is that? Nominal, right? And so functionally, when we're sitting down, we're looking at trying to look at a relation between stability of a nominal variable with a nominal variable, and then whether or not we have some 3rd factor changing the relation, the stability of this from this time to that time. If we're measuring our variables categorically, it starts to get infinitely complex in how to do it with that level of measurement, right? And so this is one of the things you want to do when you're developing research, is not just say, oh, this is how we're going to measure it here, this is how we're going to measure it here. Taking a look at that, oh, okay, well, once I do collect those, what do I do with the data once I got it, right? If I actually were to collect those data, oh, good God, now what do I do with it, right? Because that's a whole other area of data analysis in terms of working with categorical variables and looking at relations and things like that. So important, it seems, maybe sort of minutia, but as you start to get into some of this stuff, will start to make a big difference. Questions, folks, on any of that stuff? Any questions about class, expectations, anything that we've got moving forward? Okay, cool. You guys are troopers. Excited to get started with this semester. This is a fun class. It'll be taxing. You'll leave exhausted probably. I like 3 hours of statistics lectures. You might not. But again, as we go through, if you have questions, get in touch with me. Shoot me an email. Drop by my office. Talk with Tess. And want you to be very clear on this stuff. Again, don't shoot from the hip. If you have questions, ask somebody. I'll have our first assignment posted by tomorrow. You'll be able to go through and take a look at that. And again, it's just going to be questions, problems, going over some of the stuff we've got here, stuff in the Howell text. Make sure that you read those, that Howell chapter for this problem set, so that you're on track with stuff. Cool, all right, guys, thanks.